Hello and welcome to The Sleepy Scientist. It's very good to have you here. Tonight we're exploring one of the strangest questions in all of physics, whether time is truly real. First though, a brief and honest word. You've probably noticed there are no ads on these videos, so nothing will break the quiet tonight. Keeping it that way does take a little help though, and the best way to lend it is the ebook. If you have a spare minute, and only if you do, pause here and take a look. There's a QR code on screen throughout, and a link down in the description across to the website, thesleepyscientist.com. It's an unhurried, patient guide to quantum physics, the ideas behind these videos given a little more room to breathe, with the full narrated audiobook alongside. Honestly, a quiet look really is the most helpful thing you can do to keep these videos coming. That's all I'll ask tonight, and I ask it warmly. Thank you. Now before we begin, let me know where in the world you're watching from and what time it is for you. It seems obvious at first. The past is behind us, the future is ahead, and the present is where reality happens. But the deeper physics goes, the stranger time becomes. It bends with gravity, stretches with motion, points one way through entropy, and may even vanish from the deepest equations of quantum gravity. So get comfortable. Let the clocks do whatever mysterious thing clocks are doing, and let's begin with the time we feel before we ever try to measure it. Before physics ever built its great clocks, time was already there in the most intimate way possible, not as a number, not as a dial, not as a line in an equation. Time first appears to us as experience. It is the feeling that life is moving, that the present is opening in front of us and closing behind us, that one moment is arriving while another is slipping away. We do not need a laboratory to feel this. We feel it in waiting, in remembering, in growing older, in hearing a song end, in watching daylight fade from a room, or in realizing that a cup of tea has gone cold while we were thinking about something else. Everyday time feels obvious. It feels continuous, as if reality is gently flowing from one moment into the next. It feels universal, as if the same now stretches across every room, every city, every planet, and every star. It feels so natural that asking whether time is real can sound almost silly at first. Of course time is real. We wake up in it, we move through it, we lose it, waste it, measure it, chase it, and occasionally spend far too much of it wondering where we put our keys. But the time we feel is not yet the time of physics. Human time has texture. It stretches and contracts. 5 minutes can seem almost endless when we are waiting for important news. A whole afternoon can vanish when we are absorbed in something pleasant. Childhood summers can feel enormous in memory, while a routine week can pass so quietly that it leaves almost no trace. The clock may treat each second as equal, but consciousness does not always behave like a clock. The mind does not simply record time, it shapes it. This is the first important separation. Experienced time is the time of memory, attention, expectation, and awareness. Physical time is the time measured by clocks, used in equations, and tested through motion, light, gravity, atoms, and energy. These two kinds of time are connected, but they are not identical, and many of the deepest disagreements about whether time is real begin right here, in the gap between the time we live and the time physics describes. The human experience of time has a direction. We remember the past, but we do not remember the future. We anticipate tomorrow, but we do not anticipate yesterday. We see causes before effects. A glass falls, hits the floor, and breaks. We do not see broken pieces calmly leap together, rebuild the glass, and return it to the table, although that would be a useful feature in kitchens. We grow older rather than younger. Scars form after wounds. Footprints appear after someone walks across sand. This is the psychological arrow of time, the inward sense that life points one way. Memory is central to this arrow. The past feels real to us partly because it has left records. Those records may be inside the brain, or written in photographs, books, fossils, tree rings, ruins, and starlight. The future does not contain records in the same way. It appears as possibility, not as memory. So our minds arrange reality into a deeply familiar structure: what has happened, what is happening, and what may happen. Modern neuroscience suggests that this structure is not passively received. The brain actively builds a stable sense of sequence from changing information. It combines sight, sound, touch, body signals, memory, and expectation into a coherent flow. Different parts of the nervous system contribute to timing at different scales, from tiny fractions of a second to longer rhythms of attention, habit, sleep, and aging. There does not seem to be one tiny master clock in the brain, sitting somewhere behind the eyes and politely announcing each moment as it arrives. Instead, the sense of time is constructed from many processes working together. Researchers such as Carl Friston have argued that the brain is deeply predictive. In predictive processing, the brain is not merely waiting for information from the world, it is constantly generating expectations and comparing them with incoming signals. This matters for time because experience depends not only on what is happening now, but on what the brain expected to happen, what it remembers happening, and how it updates its picture of the world. Conscious time is therefore partly a story of prediction, correction, and continuity. That does not mean time is imaginary. A constructed experience can still correspond to something real. Colour is constructed by the brain from light of different wavelengths, but light is not fake. Sound is constructed from pressure waves interpreted by the auditory system, but pressure waves are real. In the same careful way, the flow of time may be a feature of conscious experience built from physical processes, even if physics later shows that time itself is not a simple flowing substance. This distinction is crucial. When physicists disagree about whether time is real, they're usually not denying that we experience time. They're asking what that experience corresponds to in the structure of nature. Is the flowing present a basic feature of the universe, or is it something produced by brains moving through a world governed by deeper laws? Is the future genuinely open, or is it part of a larger space-time structure we cannot perceive all at once? Is time fundamental, or does it emerge from change, entropy, causality, and information? The ordinary feeling of time cannot answer those questions by itself. It gives us the starting point, not the conclusion. It tells us that time is real in experience, but not whether time is fundamental in physics. It tells us that the present feels special, but not whether the universe agrees. It tells us that life seems to move forward, but not yet why forward exists. So before equations enter the story, time already has two faces. One is intimate, flowing, and psychological. The other waits to be made precise through clocks, motion, and mathematical law. Physics begins by taking the time we feel so naturally and asking whether it can be measured exactly, described universally, and placed into the machinery of nature. That was the first great ambition, to turn the private river of experience into a public clock for the cosmos. For a long time, physics treated time as the one thing everyone could agree on. Objects might move in complicated ways, planets might wander across the night sky, apples might fall from trees with suspiciously good timing. But beneath all of this motion, there seemed to be a steady background rhythm. Time was imagined as something that flowed evenly everywhere, whether anyone noticed it or not. It did not depend on a clock. It did not depend on a person watching. It did not depend on whether the universe was busy doing something dramatic or quietly minding its own business. This picture reached its most powerful form in the work of Isaac Newton. In the 17th century, Newton gave physics a structure so successful that it shaped scientific thought for more than 200 years. His great work, Philosophiae Naturalis Principia Mathematica, usually called the Principia, was published in 1687. It set out the laws of motion and universal gravitation, and it showed that the same mathematical principles could describe both ordinary objects on Earth and the movement of worlds in space. This was a profound unification. A falling stone, a cannonball, the moon, and the planets could all be understood within the same framework. The heavens were no longer a separate realm, obeying mysterious celestial rules. They were part of the same physical universe as everything else. Newton's physics made nature feel like a vast clockwork system, elegant, predictable, and deeply mathematical. At the centre of that clockwork universe was absolute time. Newton described true mathematical time as something that flows uniformly, without relation to anything external. In simpler words, time existed on its own. It passed at the same rate everywhere. It did not matter whether objects moved or stayed still. It did not matter whether the universe contained clocks, planets, people, or a single, very patient rock. Time itself would continue to flow evenly in the background. This is close to how time feels in everyday life. We imagine that there is one shared now, one universal ticking, one hidden cosmic rhythm that all clocks are trying to follow. Some clocks are better than others, of course. A modern atomic clock is rather more reliable than a kitchen clock with a weak battery, and both are more useful than guessing the time from how tired you feel, which is a brave but dangerous method. Still, we usually assume they are all measuring one underlying thing. Newton turned that assumption into a foundation for physics. In Newtonian mechanics, time is what allows motion to be described mathematically. An object has a position at a particular moment. Its velocity describes how that position changes with time. Its acceleration describes how velocity changes with time. Forces explain why acceleration happens. This gives physics a clean structure. Where is the object now? How is it moving, and where will it be later? Newton's second law made this especially clear. In spoken form, the central idea is force is equal to mass multiplied by acceleration. Acceleration means a change in motion over time, so time is not just decoration in Newton's physics. It is built into the basic description of motion itself. Gravity also depended on this universal background. Newton's law of universal gravitation said that every mass attracts every other mass, with a strength depending on the masses involved and the distance between them. In spoken form, the idea is the gravitational force between two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. With this law, Newton could explain why planets orbit the Sun, why the Moon falls around Earth instead of flying away, and why objects near Earth fall downward when unsupported. All of this required a reliable time parameter. The planets could be tracked from one moment to the next. A falling object could be predicted after 1 second, 2 seconds, or 10 seconds. The motion of the solar system could be treated as an evolving mechanical pattern. If the positions and motions of objects were known at one time, the laws could be used to calculate their future motion. This is why Newton's universe is often called clockwork. It suggested a cosmos that ran according to fixed laws, with time ticking steadily beneath the entire machine. The universe might be unimaginably large, but in principle it was orderly. Given enough information and enough mathematical skill, the future could be predicted from the present, and the past could be reconstructed from what exists now. In this view, time is real in a very strong sense. It is not merely what clocks measure. It is not just something the mind invents to organize experience. It is part of the deeper architecture of classical physics. It is the stage on which matter moves, forces act, and the universe unfolds. But even in Newton's own era, not everyone agreed. Gottfried Wilhelm Leibniz, the German mathematician and philosopher, argued against the idea of absolute time. Leibniz thought time was relational. For him, time was not an independent thing that existed by itself. It was the order of events and changes. Time described relationships, one event before another, one process after another, one motion alongside another. The difference is subtle, but enormous. Imagine a ticking clock in an otherwise empty room. Newton could say that the clock measures time because time is passing independently in the background. The clock is simply marking something that already exists. Leibniz would say that what we call time is found in the changing states of the clock itself, one tick after another, one position of the mechanism after another, one event followed by the next. Now imagine an entirely empty universe. No matter, no light, no clocks, no motion, no temperature, no particles, no events, no changes at all. For Newton, time could still pass in that empty universe. Absolute time would continue flowing, even with nothing inside it. For Leibniz, this made no sense. If absolutely nothing changes, if there are no events to order, then there is no meaningful time. Time is not a container sitting there empty. Time is the relationship between things that happen. This debate still echoes through physics. Is time like a stage on which events occur, or is it only the ordering of the events themselves? Is it a thing in its own right, or a pattern of change? Does the universe need time before anything can happen, or does time appear because things happen? Newton's view became the practical foundation of classical physics because it worked astonishingly well. It helped explain projectiles, tides, machines, falling bodies, planetary orbits, and the motion of comets. For ordinary speeds and ordinary gravitational fields, it still works beautifully today. Engineers and astronomers still use Newtonian ideas when the conditions are suitable, because a good approximation is not a failure. It is one of physics' favourite tools. But classical success did not settle the deeper question. Newton gave physics an absolute clock. Leibniz asked whether the clock was only meaningful because things changed. For centuries, Newton's picture seemed almost unbeatable. Then physicists began to study heat, disorder, and irreversible change. And slowly, the perfect clockwork universe began to reveal a new problem. If time flows evenly in the background, why does the world itself seem to move so strongly in only one direction? The clockwork universe was beautiful, but it had a problem hiding in plain sight. The problem was not that things changed. Newton's physics was excellent at describing change. It could follow a falling object, a swinging pendulum, a planet in orbit, or a comet returning after a long journey through the dark. The deeper problem was that ordinary change seems to have a direction. The world does not merely move. It appears to move one way. A hot cup of tea cools on a table. It does not become hotter while the room politely gives up some of its warmth. A dropped glass breaks into pieces. The pieces do not suddenly slide together, rebuild themselves and leap back into your hand, which would be convenient, although slightly alarming. Smoke spreads through a room. It does not gather itself neatly back into the end of a match. A drop of ink spreads through water. It does not unmix into a perfect dark bead again. Stars burn their nuclear fuel. Bodies age. Batteries run down. Perfume drifts through air. Milk poured into coffee swirls into pale brown clouds and then blends, rather than carefully separating itself later because it has reconsidered. This one-way behaviour is called the thermodynamic arrow of time. It is the direction in which heat spreads, energy becomes less concentrated, and many everyday processes become effectively irreversible. It is not the only arrow of time we experience. There is also the psychological arrow, where we remember the past and anticipate the future. There is a causal arrow, where causes seem to come before effects. But the thermodynamic arrow is one of the deepest physical clues because it connects the direction of time to heat, probability, and the structure of matter. The key concept is entropy. Rudolf Clausius introduced entropy in the 19th century while developing the science of thermodynamics. Thermodynamics began as the study of heat, work, engines, and energy, but it quickly became something much deeper. Clausius helped formulate the second law of thermodynamics, which says in broad terms that in an isolated system, entropy tends to increase. Entropy is often described as disorder, but that word can be misleading. Disorder makes entropy sound like the universe is judging your bedroom, which is unfair because the universe has many other things to worry about. More carefully, entropy is related to the number of microscopic arrangements that can produce the same large-scale state. A simple example helps. Imagine a gas in a box. If all the gas molecules are packed into one tiny corner, that is a very special arrangement. There are relatively few ways for all the molecules to be gathered together like that. But if the gas is spread evenly throughout the box, there are enormously more ways for the molecules to be arranged while still looking, on a large scale, like an evenly spread gas. The spread out state has higher entropy because many more microscopic configurations correspond to it. This is where Ludwig Boltzmann enters the story. Boltzmann developed statistical mechanics, the bridge between the motion of individual atoms and molecules and the large-scale behaviour of heat, pressure, and entropy. He showed that the second law of thermodynamics is not simply a mechanical commandment forcing every particle to behave in one direction. It is a statement about overwhelming probability. A gas spreads through a room because there are vastly more ways for its molecules to be spread out than clustered in one corner. Heat flows from a hot object to a colder one because there are vastly more ways for energy to be shared around than to remain neatly concentrated. A broken glass stays broken because there are far more ways for its fragments, sound, heat, and surrounding air to be in a scattered state than in the extremely precise arrangement of an intact glass sitting peacefully on a table. So when entropy increases, reality is usually moving from rare, special arrangements toward common, more probable arrangements. Josiah Willard Gibbs developed another powerful way to describe this kind of physics. Instead of trying to follow every single particle in an enormous system, Gibbs used statistical descriptions of large collections of possible states. This was essential because even a tiny sample of gas contains an absurd number of molecules. Tracking every particle individually would be hopeless in practice. Statistical mechanics allows physicists to describe the behaviour of the whole system without needing a microscopic diary for every atom. This is where time becomes strange again. The large-scale world clearly has a direction. Tea cools, smoke spreads, stars age. But many microscopic laws of classical mechanics work both forward and backward in time. If you imagine a few ideal particles moving and colliding, the reversed motion can still obey Newton's laws. The equations do not always come with a little arrow printed on them saying this way to the future. That creates a puzzle. If the microscopic laws are mostly time-symmetric, why is everyday experience so time-asymmetric? Why do we see glasses break but not unbreak? Why do gases spread but not spontaneously gather? Why does the universe appear to remember one direction and not the other? This question was sharpened by the Loschmidt paradox, named after Joseph Loschmidt. He pointed out that if the motions of particles could be reversed, then a system that had been increasing in entropy should be able to run backward and decrease in entropy. If the underlying laws allow both directions, where does the one-way arrow come from? The answer is subtle. The reverse process is not impossible in the simplest mathematical sense. It is just fantastically unlikely. To make a broken glass reassemble, every tiny piece, vibration, air molecule, and bit of heat would need to move in an extraordinarily precise coordinated way. The laws may permit such a reversal, but the required arrangement is so special that nature does not stumble into it under ordinary conditions. This means the arrow of time may not come from time itself as a flowing substance. It may come from probability, entropy, and the fact that the universe began in a very special low entropy state. The past was more ordered in a precise statistical sense. The future is the direction in which there are more possible microscopic arrangements available, and this brings us back to the question of whether time is real. If time is real, one of its most obvious features seems to be direction. We do not experience life as a neutral line that can be travelled both ways. We experience it as a one-way unfolding. Yet physics struggles to explain whether that direction belongs to time itself, or whether it emerges from matter, energy, probability, and the early condition of the cosmos. The clock still ticks forward. But now the ticking is not enough. The world has an arrow, and that arrow seems to be made not from time alone, but from heat, statistics, and the quiet mathematics of things becoming more likely. And the mystery becomes even sharper when Einstein removes the idea of one universal cosmic clock altogether. The next great break in the story of time came from light, not from clocks directly, not from aging, heat, or broken glasses. From light, moving through empty space with a speed that refused to behave like ordinary speeds. It was this refusal that quietly began to dismantle Newton's universal clock. In the 19th century, James Clerk Maxwell brought electricity and magnetism together into one theory: electromagnetism. Before Maxwell, electric and magnetic effects had often been treated as related but distinct phenomena. Maxwell's equations showed that they were deeply connected. A changing electric field could produce a magnetic field, and a changing magnetic field could produce an electric field. Together, these changing fields could travel as a wave. When Maxwell calculated the speed of those electromagnetic waves, the value matched the known speed of light. This was a profound discovery. Light was not just something that helped us see things before bumping into them in the dark. Light was an electromagnetic wave. But this created a problem. Waves usually seem to need a medium. Sound travels through air. Ripples travel through water. So physicists assumed that light must travel through some invisible substance filling space. They called it the luminiferous ether. This ether was imagined as a kind of hidden cosmic medium, the thing light waved through as it crossed the universe. If the ether existed, Earth should be moving through it as it orbited the Sun. And if Earth moved through it, then light should appear to travel at slightly different speeds depending on its direction. Light moving with Earth's motion through the ether should behave differently from light moving against it, or sideways through it. In 1887, Albert Michelson and Edward Morley tested this idea in one of the most famous experiments in physics. Their Michelson-Morley experiment used an interferometer, a device that split a beam of light into two paths and then recombined it. If light travelled at different speeds in different directions because of Earth's motion through the ether, the experiment should have revealed a tiny shift in the interference pattern. But the expected shift did not appear. The result was deeply unsettling for classical physics. It was not loud or dramatic, it was almost worse than that. It was quiet, precise, and stubborn. The ether, which had seemed like a sensible explanation, began to disappear from serious physics. Then, in 1905, Albert Einstein proposed the special theory of relativity. Einstein began with two principles. The first was that the laws of physics are the same for all observers moving at constant velocity. These are called inertial observers. The second was that the speed of light in a vacuum is the same for all inertial observers, no matter how the light source or observer is moving. This sounds simple, but it changes almost everything. In ordinary life, speeds add together. If you walk forward inside a moving train, someone standing beside the track combines your walking speed with the speed of the train. If you throw a ball forward from that train, its speed relative to the ground is affected by the train's motion. This is how common sense expects the world to work. Light does not follow that rule. If a spaceship moving very fast shines a beam of light forward, an observer still measures that light travelling at the same speed of light. Not the speed of light plus the spaceship's speed. Not the speed of light minus the observer's speed. Just the speed of light. Something had to give. And what gave was the old belief that space and time are absolute. Einstein showed that observers moving relative to each other can disagree about lengths, durations, and simultaneity, while still agreeing on the laws of physics and the speed of light. Time was no longer a single universal background flowing identically for everyone. Time became linked to motion. The clearest example is time dilation. A moving clock is measured to run slow relative to an observer. This does not mean the clock is badly made. It does not mean the hands are sticky, the gears are sulking, or the battery needs replacing. It means that time itself is measured differently for objects in different states of motion. At everyday speeds, this effect is tiny. Walking to the shop does not make you noticeably younger than someone who stayed at home, which is a shame, because it would make light exercise much more popular. But as speeds approach the speed of light, time dilation becomes dramatic. A clock moving very fast can record less elapsed time than a clock that remains behind. The spoken form of the time dilation equation is: the time measured by a moving observer is equal to the stationary time divided by the square root of 1 minus the speed squared divided by the speed of light squared. This equation expresses a startling idea. Time depends on motion. There is no single master clock shared by the entire universe. Special relativity also introduced the relativity of simultaneity. Two events that appear to happen at the same time for one observer may not happen at the same time for another observer moving differently. This is not a trick of perception. It is not caused by delayed information in the ordinary sense. It is built into how space and time fit together when the speed of light is fixed. Einstein often explained this with thought experiments involving trains and lightning. Imagine lightning striking both ends of a moving train. An observer standing beside the track may judge the strikes to be simultaneous, but an observer on the train is moving toward the light from one strike and away from the light from the other. Because both observers measure light as travelling at the same speed, they can disagree about whether the two strikes happened at the same time. This disagreement reveals something profound. There is no universal now that every observer must share. The twin paradox makes the same lesson more personal. One twin stays on Earth, while the other travels through space at extremely high speed and then returns. The travelling twin can come back younger than the twin who remained on Earth, because less time has passed along the traveller's path. This is not a true contradiction. The travelling twin changes direction, accelerates, and shifts between inertial frames, so the two twins do not have symmetrical journeys. Still, the result is astonishing. Two people can reunite after experiencing different amounts of time. Einstein did not prove that time is unreal. In fact, he made time more physically serious than ever. Time could stretch. It could differ between observers. It could no longer be separated from motion, light, and measurement. So the question of whether time is real became harder, not easier. Time still exists in the equations. Clocks still measure it. Bodies still age through it. But it is not the universal independent flow that Newton imagined. It is stranger than common sense expects. Flexible, observer-dependent, and deeply woven into the behaviour of light itself. Einstein had already made time less universal than common sense expected, but the next step made the picture even stranger, because special relativity did not merely show that clocks can disagree. It suggested that space and time are not truly separate ingredients of reality. They are different aspects of one deeper structure. In 1908, the mathematician Hermann Minkowski gave Einstein's special relativity its most powerful geometric form. Minkowski had once been one of Einstein's teachers, and he saw that the strange effects of relativity could be understood more clearly if space and time were joined together. Instead of thinking of the universe as three-dimensional space evolving through a separate flow of time, Minkowski described a four-dimensional structure called spacetime. In this picture, space and time are woven into a single geometric framework. That may sound abstract, but the basic idea is gentle enough. In ordinary space, an object can be located using three directions: left and right, forward and backward, up and down. But an event needs more than a place. It also needs a time, a firework exploding, a clock ticking, a star emitting light. A door closing or a cup landing on the floor is not fully described by saying where it happened. We also need to say when it happened. So an event in space-time is like a location in a four-dimensional map. It has 3 dimensions of space and 1 dimension of time. The event does not just happen somewhere. It happened somewhere and somewhen. This was a major change in how physicists imagined reality. Before relativity, it felt natural to think of space as the stage and time, as the flow in which things changed on that stage. But Minkowski's interpretation suggested that different observers moving relative to one another are not simply disagreeing because one has made a mistake. They are dividing the same four-dimensional reality into space and time in different ways. One observer may measure a certain distance between two events. Another observer, moving differently, may measure a different distance and a different duration. Special relativity allows this, but something deeper remains consistent. That deeper quantity is called the spacetime interval. The spacetime interval is a combination of the separation in space and the separation in time between two events. Different observers may disagree about the spatial distance and the time duration separately, but they agree on the spacetime interval. It is the part of the geometry that stays fixed beneath their different measurements. A simple comparison is a shadow, though it is only a comparison. A three-dimensional object can cast different two-dimensional shadows depending on how it is turned toward the light. The shadows may change shape, but the object itself has not changed. In a similar spirit, observers moving differently can slice space-time into space and time differently, while the underlying space-time relationship remains the same. The analogy is imperfect, but it helps reveal the point. Relativity is not just about confusion between observers. It is about a deeper structure they are all describing from different angles. This is where the block universe enters the story. The block universe is an interpretation of relativity also known as eternalism. It suggests that space-time may be understood as a complete four-dimensional whole, where past, present and future are all part of the same structure. In this view, the present moment is not physically privileged in the way it feels to us. The past does not vanish into nothing, and the future is not simply absent. Instead, all events may belong to the full space-time block. This does not mean we experience all moments at once. We clearly do not. We experience waking up, getting older, remembering yesterday, and wondering what tomorrow will bring. We live along a path through space-time, and our minds arrange that path into the familiar feeling of passage. But eternalism suggests that the whole path may exist within space-time, rather than being created moment by a moving universal present. It is important to be careful here. The block universe is not a laboratory result in the simple sense. No one has placed the universe on a table, tapped it gently, and confirmed that it is definitely a block, which would be difficult for several reasons, including the shortage of tables large enough. The block universe is an interpretation encouraged by the structure of relativity, especially by the loss of universal simultaneity. The equations of relativity are extremely well tested. The philosophical meaning of those equations is where the debate begins. The difficulty comes from the ordinary feeling that time flows. In daily life, the present feels special, the past feels fixed, the future feels open. We do not feel like static parts of a four-dimensional pattern. We feel like beings moving through a changing world. We make choices, wait for outcomes, remember what has happened, and watch events unfold. The block universe challenges that feeling. If all events in space-time are equally real, then time may not flow in the deepest physical sense. The entire history of reality may simply exist as a four-dimensional structure. What we call the passage of time may be connected to consciousness, memory, entropy, and the direction along which physical records accumulate. This is why the idea has troubled philosophers and physicists for more than a century. J.M.E. McTaggart argued that time, as we ordinarily understand it through past, present, and future, contains deep conceptual problems. Later thinkers such as Hugh Price explored how the direction of time in physics may be tied to our perspective within the universe rather than to a simple built-in flow. These debates can become philosophical, but they remain close to physics because relativity itself makes the old idea of one shared present difficult to defend. So is time real in Minkowski's spacetime? In one sense, yes. Time is part of the geometry of the universe. Clocks measure it. Motion affects it. Observers use it to locate events. But in another sense, the flowing time we feel may not be fundamental. The present may not be a cosmic spotlight sweeping across existence. It may be a feature of how conscious systems experience their path through space-time. Minkowski did not remove time from physics. He gave time a deeper and stranger home. Time became part of space-time, joined to space in a four-dimensional structure that all observers describe in their own way. And the story was not finished, because Einstein's later theory of general relativity would make space-time even more physical. It would not merely be the map of events, it would bend, stretch, and curve in the presence of mass and energy. Einstein's special theory of relativity had already weakened the old idea of a universal clock. But general relativity went further. It did not simply say that motion changes how time is measured. It said that gravity changes time as well. In 1915, Albert Einstein presented his general theory of relativity, a new theory of gravity. In Newton's picture, gravity was a force pulling masses toward one another across space. Earth pulled on the moon. The sun pulled on Earth. Every object with mass attracted every other object with mass. It was powerful, elegant, and extremely useful. But Einstein described gravity in a different way. Gravity was not a conventional force acting through space. It was the curvature of space-time itself. Mass and energy shape space-time, and objects move by following the curved paths that space-time makes available to them. A planet orbiting the sun is not being tugged by an invisible rope. It is moving through curved space-time, following the natural path created by the sun's mass and energy. This changed time again, because space-time includes time. If gravity curves space-time, then gravity also affects the ticking of clocks. This effect is called gravitational time dilation. A clock deeper in a gravitational field ticks more slowly, compared with a clock farther away from the source of gravity. A clock near Earth's surface ticks slightly more slowly than a clock high above Earth. The difference is tiny in ordinary life, but it is real. It has been measured many times, and it is not a flaw in the clocks. It is a feature of time itself in curved space-time. A useful way to imagine it is to think of gravity not only as something that bends the paths of objects, but also as something that changes the rhythm of time. Near a massive object, time runs a little slower. Farther away, where gravity is weaker, time runs a little faster. This is not because clocks are tired near planets, although one could forgive them. It is because the geometry of space-time is different. The effect becomes important in technologies we use every day. The global positioning system depends on satellites orbiting high above Earth. Those satellites carry extremely accurate atomic clocks. Because they are moving relative to clocks on the ground, special relativity makes their clocks tick slightly slower. But because they are farther from Earth's gravitational field, general relativity makes their clocks tick faster. The two effects do not cancel exactly. The faster ticking from weaker gravity is larger than the slower ticking from orbital motion. If engineers did not correct for both effects, the global positioning system would drift by kilometers over time. A phone map would slowly become less a navigation tool and more a confident little liar. So every time satellite navigation works, it is quietly using the fact that time is not universal. Time is shaped by motion and by gravity. One important early test of this idea was the Pound-Rebka experiment at Harvard University in 1959. Robert Pound and Glenn Rebka tested gravitational redshift, which is closely connected to gravitational time dilation. They measured how the frequency of gamma rays changed as the radiation moved through Earth's gravitational field over a height of about 22 meters inside a tower at Harvard. The effect was incredibly small but measurable. It showed that gravity affects the frequency of light, just as general relativity predicted. This matters because frequency is a kind of clock. Light waves oscillate. If gravity changes the frequency of light, then gravity is changing the rate at which that physical process unfolds. Once again, time is not standing apart from the universe as a perfect background. It is participating in the structure of reality. Black holes make the effect far more extreme. A black hole is a region where gravity is so strong that, within a boundary called the event horizon, not even light can escape. The first exact solution to Einstein's field equations describing a simple, non-rotating black hole was found by Carl Schwarzschild in 1916, shortly after general relativity was completed. His work revealed what is now called the Schwarzschild radius, the size of the event horizon for a non-rotating black hole of a given mass. Near a black hole, gravitational time dilation becomes enormous. To a distant observer, a clock falling toward the event horizon would appear to slow down more and more as it approached that boundary. The falling clock would seem to fade and redshift. Its light stretched to longer wavelengths, while its ticking appeared increasingly delayed. From far away, it would look as though time near the event horizon is almost freezing. For the falling observer, however, their own clock would tick normally. They would not feel their wristwatch dramatically losing interest in existence. They would cross the event horizon in a finite amount of their own time, at least for a large enough black hole where tidal forces at the horizon are not immediately destructive. This difference between the distant observer and the falling observer is another sign that time is not simple or universal. General relativity therefore deepens the disagreement about time. Time is not just observer-dependent because of motion. It is physically shaped by gravity. It runs differently at different heights, near different masses, and along different paths through curved space-time. The old idea of one cosmic clock ticking evenly everywhere becomes harder and harder to defend. And yet, time has not disappeared. In relativity, time becomes part of geometry. It is woven into space-time, affected by mass, energy, motion, and curvature. It is real enough to guide satellites, bend light, shape black holes, and change the aging of clocks. But physics was about to complicate the story again. Because while relativity gives time a geometric role, quantum mechanics gives time a very different one. Relativity made time part of the geometry of the universe. Quantum mechanics treats it very differently. This is one of the reasons physicists still cannot agree on what time really is. In one great theory, time is woven into space-time, shaped by motion and gravity, curved by mass and energy. In another great theory, time often sits outside the system, almost like a quiet background clock used to describe how quantum possibilities change. Quantum mechanics emerged in the early 20th century because atoms and light refused to behave like ordinary objects. Max Planck opened the door when he proposed that energy could be exchanged in discrete packets. Albert Einstein used the idea of light quanta to explain the photoelectric effect. Niels Bohr applied quantum ideas to the atom. Werner Heisenberg developed matrix mechanics. Erwin Schrödinger introduced wave mechanics. Max Born gave the wave function its probabilistic meaning. Paul Dirac built a deeper mathematical framework that helped connect quantum mechanics with special relativity. Wolfgang Pauli explained the exclusion principle, which helps give atoms their structure. Together, these ideas created a theory that describes the microscopic world with astonishing success. Quantum mechanics explains atomic spectra, chemical bonds, semiconductors, lasers, magnetic materials, radioactive decay, and much of the technology quietly surrounding modern life. It is not a vague theory about things being mysterious for the sake of it. It is one of the most accurate and useful frameworks in all of science. But its treatment of time is peculiar. In ordinary non-relativistic quantum mechanics, time is not usually treated like position or momentum. Position can be measured as an observable. Momentum can be measured as an observable. Energy can be represented by an operator, but time usually appears as an external parameter. It is the thing used to label how the quantum state changes. It is not normally something the quantum system possesses, in the same way it may possess measurable position, momentum, or spin. This sounds technical, but the idea is simple enough. Imagine describing a particle. Quantum mechanics gives that particle a wave function, which represents the possible outcomes of measurements and the probabilities associated with them. The wave function changes as time passes. Time is the background variable against which that change is described. The central rule for this change is the Schrödinger equation. In spoken form, the idea is the change of the wave function with time is determined by the total energy operator acting on the wave function. That sentence carries a large amount of physics. The wave function contains information about possible states. The total energy operator, often called the Hamiltonian, tells the wave function how to evolve. As time passes, the wave function changes smoothly and predictably according to this rule. In this sense, quantum mechanics can be extremely orderly. It does not say that tiny things are simply doing whatever they like because they are very small and have become overconfident. The evolution of the wave function is precise, given the starting wave function and the correct energy operator. The theory tells us how the wave function develops over time. The strangeness appears when measurement enters. Before measurement, a quantum system can be described as a superposition of possible outcomes. An electron might not have one definite position in the ordinary classical sense. An atom might have several possible energy-related behaviors encoded in its quantum state. The wave function evolves smoothly, spreading and interfering according to the Schrödinger equation. But when a measurement is made, we obtain one definite result. A detector clicks in one place. An atom is found in one energy state. A particle leaves a mark on a screen. The smooth spread of possibilities gives way to a single outcome. This is the measurement problem. The difficulty is not that quantum mechanics fails to predict experiments, it predicts them extraordinarily well. The difficulty is understanding what physically happens during measurement. Does the wave function really collapse? Is collapse a real physical process, or only an update in our knowledge? Are all possible outcomes realized in different branches, as in the many worlds interpretation associated with Hugh Everett? Does the measuring device become entangled with the system? Does the environment explain the appearance of definite outcomes through decoherence? A study by researchers such as H. Dieter Zeh and Wojciech Zurek. The status of time becomes tangled in this problem. Smooth quantum evolution happens in time. Measurement seems to produce a definite event in time. Probability describes possible futures before measurement, while a record appears afterward. The before and after of measurement feels deeply connected to the arrow of time, to information, and to the way physical events become part of the world we can observe. This is already different from the role time plays in relativity. In relativity, time is part of the physical fabric. It mixes with space. It stretches with motion. It slows in gravity. In quantum mechanics, at least in its ordinary non-relativistic form, time often functions more like an external clock. It is not curved by the particle being studied. It is not usually treated as a quantum observable. It is simply there, marking the evolution of the wave function. That creates a deep tension. General relativity says space-time is dynamic. Matter and energy influence its geometry. Quantum mechanics often assumes a fixed background time in which quantum systems evolve. One theory makes time part of the stage that can bend and change. The other often uses time as if the stage were already in place. For most practical purposes, this is not a problem. If a physicist is calculating the behavior of an electron in an atom, ordinary quantum mechanics works beautifully. If an engineer is designing a semiconductor device, they do not usually need to solve the deepest philosophical problem of time before breakfast. Fortunately for breakfast, physics allows approximations. But at the most fundamental level, especially when trying to combine quantum mechanics with gravity, the difference becomes unavoidable. If space-time itself is supposed to be quantum, then what time does the quantum state evolve through? If the whole universe is the quantum system, what external clock is left outside it? This is why quantum mechanics does not merely complicate what happens in time. It raises the sharper possibility that time may not belong in the deepest description in the way we expect. Perhaps time is fundamental, perhaps it is emergent, perhaps it is a parameter that works in ordinary quantum theory, but must be replaced by something deeper when gravity is included. The clocks still tick, measurements still happen, atoms still change state. But beneath those familiar facts, quantum mechanics leaves time looking strangely unfinished, as if one of the most important words in physics has not yet received its final definition. There is one part of time that feels almost impossible to doubt: now. Whatever else physics says, the present moment feels immediate. The past feels gone. The future feels not yet here. We may remember yesterday and imagine tomorrow, but we seem to live only in the present. It feels like the sharp edge of reality, the place where the universe is actually happening. Everything else is either memory or possibility. This is one reason the question of whether time is real becomes so personal. It is not only about clocks, equations, planets, or particles. It is about the strange feeling that this moment is special. Not just special to us emotionally, but physically special. The present seems to have a kind of brightness that the past and future do not. Relativity makes this difficult. In ordinary life, it feels natural to imagine one universal now. We picture the present as something spread across the cosmos, passing through Earth, the Moon, the Sun, distant stars and galaxies far beyond sight. While you're here, listening in this moment, it seems obvious that something else is happening right now on Mars, around Alpha Centauri, and in a galaxy a billion light-years away. The universe feels as if it shares one giant present tense. But special relativity says simultaneity depends on motion. Two events that are simultaneous for one observer may not be simultaneous for another observer moving differently. This is not a delay caused by slow messages or poor cosmic scheduling. It is built into the structure of spacetime. Once the speed of a light is fixed for all observers, different states of motion slice spacetime into space and time in different ways. That means the idea of a universal present becomes hard to define. Imagine two distant events, perhaps one flash of light near Earth and another flash in a faraway galaxy. One observer may calculate that the two flashes happened at the same time. Another observer, moving relative to the first, may calculate that one happened before the other. A third observer, moving differently again, may disagree with both. None of them is simply wrong. They're using different valid frames of reference. This becomes even more dramatic across cosmic distances. Light from the Andromeda galaxy takes about 2.5 million years to reach us. When we look at Andromeda, we're seeing it as it was about 2.5 million years ago, long before human civilization, before cities, before written language, before anyone could misplace a phone charger and feel personally betrayed by the universe. What is happening in Andromeda now sounds like a simple question, but physics makes it slippery. Because over such distances, and with different possible observers in motion, there may be no single objective now that everyone must agree on. This is where different views of time begin to separate. Presentism is the view that only the present is real. The past no longer exists. The future does not yet exist. Reality is just the moving present moment. This view fits very naturally with human experience. It feels close to how life appears from the inside. Yesterday is memory. Tomorrow is expectation. Only now seems fully alive. Eternalism gives a very different answer. In eternalism, past, present, and future are all equally real within space-time. The present is not an objectively privileged slice of the universe. It is more like a perspective from within a four-dimensional structure. Just as different places exist even though we are only standing in one location, different times may exist even though we are only experiencing one moment along our path. The block universe is the usual physical image connected with eternalism. It treats space-time as a complete structure, containing all events. The birth of stars, the formation of Earth, your earliest memory, this present sentence, and events far in the future would all belong to the full spacetime pattern. We do not experience the whole structure at once, but that does not mean only the moment we experience exists. There is also an intermediate view called the growing block universe. In this view, the past and present are real, but the future is not yet real. Reality grows as time passes. New events are added to the block while the past remains part of existence. This view tries to preserve something from ordinary experience, especially the sense that the future is open, while avoiding the idea that the past simply disappears into nothing. These views can sound like philosophical word games, but they are not empty. Each is trying to make sense of a genuine tension. Experience tells us that the present feels special. Relativity tells us that there may be no universal present shared by all observers. Physics gives us equations that work beautifully, while consciousness gives us the unavoidable feeling of living in a now. Importantly, physicists can agree on measurable predictions while disagreeing about what those predictions imply. They can agree that special relativity predicts time dilation and the relativity of simultaneity. They can agree that experiments confirm these effects, but they may still disagree about whether this means eternalism is true, whether presentism can be reformulated, or whether our ordinary idea of the present is something emerging from deeper physical and psychological processes. That is why the disagreement about time is often really a disagreement about the present moment. Does the present have objective physical status? Or is it a feature of our perspective as beings who remember in one direction and anticipate in the other? Is now a basic ingredient of the universe, or only the place where a conscious system finds itself along a path through space-time? Physics has not settled this in a way that makes everyone happy. The present is obvious in experience, but elusive in relativity. It is the most familiar thing in life, yet one of the hardest things to locate in the fundamental description of nature. And even if we ask whether the present exists, another mystery waits just behind it. Because the present does not merely seem to exist, it seems to move. Time does not feel like a still landscape, it feels like a flow. Time feels as though it flows. That may be the most natural thing anyone can say about it. The present seems to move. Yesterday appears to fall behind us. Tomorrow seems to approach. We do not usually experience time as a still line or a fixed structure. We experience it as passage, as becoming, as the quiet forward movement of reality itself. But physics is unusually cautious about this feeling. Many physical equations describe relationships between events without adding a separate ingredient called flow. They may say how a system changes between one state and another. They may describe the interval between two events, the motion of a planet, the decay of a particle, or the ticking of a clock. But they do not usually include a mysterious current that carries the universe forward. There is no obvious extra substance in the mathematics labelled the flow of time, gently pushing everything from past into future like a very responsible cosmic river. A clock measures intervals. It compares one repeated process with another process. The swing of a pendulum can be compared with the motion of a shadow. The rotation of Earth can be compared with the orbit of the Moon. The vibration of a cesium atom can be used to define the second with extraordinary precision. But in each case, the clock is not directly measuring a flowing liquid called time. It is measuring regular change and using that change to compare other changes. This distinction matters. Time as a dimension is not the same idea as time as a process. In relativity, time can be treated as part of space-time, one dimension woven together with the three dimensions of space. Events can be ordered, intervals can be calculated, and different observers can measure different durations. But a dimension does not obviously flow. A road does not flow just because we travel along it. A landscape does not rush past in its own right just because a walker moves through it. This is where some of our language may mislead us. We say time flows. We say time passes. We say time moves. But perhaps these phrases come from human experience rather than from the deepest structure of physics. Perhaps it is not time that flows, but our consciousness that moves from one experienced state to another. Or perhaps even that wording is too strong, because in a block universe there may be no moving consciousness in an absolute sense, only a sequence of conscious moments ordered along a path through space-time. One of the most famous arguments about this came from the philosopher J.M.E. McTaggart. He argued that our ordinary idea of time depends on what he called the A series, events being future, then present, then past. In the A series, an event changes its status. A birthday is future, then it is present, then it is past. This captures the feeling of passage. McTaggart contrasted this with the B series, where events are ordered only by relations such as earlier than and later than. The birth of Isaac Newton is earlier than the publication of Philosophiae Naturalis Principia Mathematica. The publication of that book is earlier than Einstein's special theory of relativity in 1905. These relations do not change. If one event is earlier than another, it remains earlier than another. The B series gives an ordered structure, but not the moving present. McTaggart argued that the A series contains deep contradictions, because events would have to possess incompatible properties of being future, present, and past. His conclusion was that time, at least as ordinarily understood, is unreal. Many philosophers and physicists have disagreed with parts of his argument, but the distinction remains useful. It separates the time of passage from the time of ordering. Physics often looks more comfortable with the B series. Relativity, especially, describes events in space-time and the relations among them. It does not give us a universal presence sweeping across the cosmos. It does not identify one privileged moving now that everyone must share. For that reason, many physicists hesitate to treat the flow of time as fundamental. The equations work without needing a cosmic spotlight that moves from past to future. The block universe gives one way to picture this. Reality may be like a complete film reel, with every frame existing as part of the whole. We experience the movie one frame at a time, but the reel itself is not being created one frame at a time. This analogy helps explain eternalism, but it can also mislead. A film reel sits inside another time, where a projector runs and an audience watches. The universe does not obviously sit inside a larger external time with something outside it pressing play. The river analogy is also tempting. Time seems to carry us forward like water carrying a leaf. This captures the feeling beautifully. But rivers flow through space over time. If time itself flows, what does it flow through? And how fast would it flow? 1 second per second sounds meaningful at first, but it does not explain much. It is a little like saying a road extends at 1 meter per meter. True, perhaps, but not the kind of statement that opens many locked doors. Another analogy is a path through a landscape. The path may already exist, while a walker experiences it step by step. This helps with the block universe picture, because different locations on the path are like different events in space-time. But again, the analogy depends on a traveller moving through an external time. In physics, the traveller and the path are both part of the universe being described. Still, it may be too quick to dismiss passage as merely psychological. Some thinkers argue that the flow of time is too central to experience, causation, decision-making, and physical becoming to be brushed aside. We do not live as if all moments are equally present to us. We act, choose, remember, anticipate, and respond. The difference between a possibility and an accomplished fact feels like more than a grammatical preference. This is why the debate remains alive. Physics can describe ordered events with immense precision, but the felt passage of time is harder to place. Perhaps flow is not fundamental. Perhaps it emerges from the way conscious systems form memories. Perhaps it comes from entropy, because records accumulate in one direction and not the other. Perhaps it is tied to causality, information, and the fact that the universe began in a very special low entropy state. So does time flow, or do we move through it? The safest answer is that our experience of flow is real as experience, but physics has not clearly identified a fundamental flowing substance called time. Clocks measure intervals, relativity orders events, spacetime can be mapped, but the moving present remains elusive. The best physical clue may be the arrow of time. If time feels like it flows, perhaps that feeling is not caused by time alone, but by entropy, memory, records, and irreversible processes. The world points one way, and because we are part of that world, our minds may turn that direction into the feeling of passage. Yesterday feels different because yesterday left evidence behind. It left traces in memory, marks in the world, and records in matter. A footprint pressed into soft ground, a photograph saved on a phone, a fossil held inside rock, a scar formed in skin, starlight crossing space, a sentence written on a page. These are not just poetic images, they are physical clues to the arrow of time. The past feels fixed partly because the past has records, the future does not. We can remember what happened yesterday because yesterday changed the physical world in ways that survived into today. But we do not remember tomorrow, because tomorrow has not left records here yet. There are no future fossils waiting politely in the cupboard. There are no photographs of next week hiding in the camera roll, unless something has gone very wrong with both physics and your phone. This is where entropy becomes deeply connected to memory. A memory is not a floating ghost of the past. It is a physical arrangement in the brain. When we form a memory, neurons change their connections. Chemical signals are altered, proteins are produced, and networks of cells become more likely to activate in certain patterns again. Those changes require energy. They involve heat. They are part of irreversible physical processes. The brain can store information, but it does so as a living, warm, energy-using object inside the universe. And because the brain is physical, memory is tied to the second law of thermodynamics. To make a record, the world must change in a way that distinguishes before from after. Light must hit a camera sensor. Ink must dry on paper. A footprint must deform sand. A fossil must form through mineral replacement and geological pressure. A scar must grow as tissue repairs itself. Each record is a physical event that uses energy and usually increases entropy overall, even if it creates a local pocket of order. This is why we remember the past and not the future. Records form from earlier events and persist into later states. The direction in which records accumulate is the same direction in which entropy increases. We know about yesterday because yesterday helped produce the present. We do not know tomorrow in the same way because tomorrow has not yet produced physical traces in the present. Cause and effect point the same way. A stone falls into a pond and ripples spread outward. A match is struck and smoke rises into the air. A star burns nuclear fuel and radiation streams into space. Causes leave effects. Effects become records. Records support memory. Memory gives us the psychological arrow of time. Beneath the feeling of I was there lies a chain of physical changes that cannot simply be reversed in ordinary circumstances. This does not mean that the past is easy to reconstruct perfectly. Records can fade, break, distort, or vanish. Memories can be unreliable. Fossils can be incomplete. Radiation can be absorbed or scattered. The universe is not an immaculate filing cabinet. It is more like a very large, very old archive that occasionally drops tea on its own paperwork. But the basic asymmetry remains. We find traces pointing backward, not forward. The deeper question is why the universe allows this arrow at all. Entropy tends to increase only because there was lower entropy before. If the universe had always been in a state of maximum entropy, there would be no useful arrow, no strong contrast between past and future, no stars burning, no life-forming records, and no cups of tea cooling down in a meaningful thermodynamic direction. The arrow of time points away from a special past. This brings us to one of the strangest facts in cosmology. The early universe was extremely hot. extremely dense and remarkably smooth. At first, that might sound like a high entropy state because hot, dense matter sounds rather chaotic, but gravity changes the story. When gravity matters, smoothness can actually represent a very special low entropy condition. A universe where matter is spread almost evenly is gravitationally unusual. Over time, gravity pulls matter into clumps, forming galaxies, stars, planets, black holes, and all the cosmic structure we see today. Roger Penrose has emphasized this puzzle. He argued that the early universe was extraordinarily low entropy when gravity is properly included. The smoothness of the early cosmos was not ordinary. It was deeply special. In Penrose's view, the initial state of the universe was so improbable that it demands explanation. This does not mean we currently have a final answer. It means the arrow of time may be rooted in the boundary conditions of the universe itself. Boundary conditions are the starting or limiting conditions that shape how physical laws unfold. The microscopic laws may not always contain a built-in direction of time, but if the universe begins in a very special low entropy condition, then the later development naturally has a direction. Entropy can rise because it had somewhere to rise from. Cosmology gives us evidence for that early state. The cosmic microwave background is the afterglow of the early universe released when the cosmos cooled enough for light to travel freely through space. Arno Penzias and Robert Wilson detected this radiation in the 1960s. Later, the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck Space Observatory mapped it in extraordinary detail. These observations show a universe that was once hot, dense, and astonishingly uniform, with tiny variations that later grew into galaxies and clusters. Those tiny variations matter. They were the seeds of cosmic structure. But the overall smoothness matters too because it tells us the early universe was not just any random state. It was a very special one. The arrow of time may therefore be less like a local rule stamped onto every particle, and more like a cosmic inheritance from the beginning. This helps explain why yesterday feels different. Yesterday is closer to the lower entropy past. It left records that persist into today. Today contains traces of yesterday, while tomorrow does not yet contain traces reaching backward into us. Memory, aging, causation, fossils, radiation, and history all lean in the same direction because they are part of a universe moving away from a special early condition. But this still does not prove that time itself flows as a fundamental substance. Entropy may explain why time has an arrow without explaining whether time is a river. It may show why events are ordered, why records exist, and why memory faces one way, while leaving open the deeper question of whether time is fundamental, emergent, or something else entirely. The mystery has now grown larger than clocks, brains, and broken glasses. It reaches back to the beginning of the observable universe. To understand why time points one way, physics has to ask why the cosmos began in a state from which one way was possible at all. The arrow of time points back toward a very old question. If the universe has a history, did time itself have a beginning? Modern cosmology says that the observable universe has evolved from a much hotter, denser, earlier state. This does not mean the Big Bang was an explosion inside empty space. It was not matter flying outward into a pre-existing cosmic room. It was the expansion of space itself, carrying matter and radiation with it, changing the density and temperature of the universe as it grew. In standard cosmology, time is used to describe that history. The universe was once hotter, then it cooled. Light nuclei formed, atoms formed later. Gravity gathered matter into galaxies. Stars were born, lived, and died. Planets formed from heavy elements made inside earlier generations of stars. Eventually, after a long chain of cosmic events, there were warm little creatures on one small planet asking whether time is real, which is an impressive level of curiosity from matter that was once mostly hydrogen. The idea of an expanding universe emerged from both theory and observation. Alexander Friedmann, working with Einstein's general theory of relativity, found mathematical solutions in which the universe could expand or contract. The Friedmann equations became a foundation for modern cosmology because they describe how the scale of the universe changes depending on its contents, including matter, radiation, curvature, and what is now called dark energy. Georges Lemaitre, a Belgian physicist and priest, also developed the idea of an expanding universe and proposed that the cosmos may have evolved from what he called a primeval atom. Lemaitre understood that general relativity did not require a static universe. Space itself could change with time. Then observations gave the idea power. Edwin Hubble studied distant galaxies and found that many were receding from us, with more distant galaxies generally showing greater redshift. Redshift means that light is stretched toward longer wavelengths, and in cosmology, it is a sign that space has expanded while the light travelled. The farther away a galaxy is, the longer its light has usually been travelling, and the more the expansion of space has stretched that light. This changed the picture of cosmic history. If galaxies are generally moving away because space is expanding, then in the past the universe was smaller, hotter, and denser. Running the story backwards suggests an early state where ordinary matter, radiation, space, and time were compressed into conditions far beyond everyday experience. That is the Big Bang model. It is important to say carefully what this model does and does not mean. The Big Bang is not a firework going off in a dark void. It is not a central explosion with galaxies flying outward from one special location. Every region of space was once hotter and denser. The expansion happened everywhere. The Big Bang describes the early hot, dense phase of the universe and its later evolution, not a blast from a point into already waiting emptiness. But if the universe can be traced back to an early hot, dense state, the question becomes unavoidable. Did time begin there? Classical general relativity gives a troubling answer. If its equations are pushed backward far enough under ordinary assumptions, they point toward a singularity, a condition where density, curvature, and temperature become infinite, and the theory itself stops giving a sensible physical description. A singularity is not just a place where something dramatic happens. It is a sign that the theory has reached the edge of its own usefulness. So when people say time began at the Big Bang, they're often referring to this classical picture. If space-time itself is part of the universe, and if classical relativity traces space-time back to a boundary, then asking what happened before that boundary may be like asking what is north of the North Pole. The question sounds grammatical, but it may not point to a real direction. However, that answer is not final. The early universe was so extreme that quantum effects and gravity should both matter. Classical general relativity does not include quantum mechanics, so the singularity may not be a real physical point where everything becomes infinite. It may be a warning sign that we need a theory of quantum gravity. Different models give different possibilities. In some, time genuinely begins with the universe. In others, there may have been a previous phase, a bounce, a larger multiverse, or some deeper structure from which our expanding universe emerged. These ideas are not all equally developed, and none has replaced the standard Big Bang model with a fully confirmed theory of the beginning. But they show why the question of before is still open. Stephen Hawking and James Hartley proposed one famous idea called the no-boundary proposal. In this speculative quantum cosmology model, the universe does not begin with a sharp boundary in time in the ordinary sense. Near the beginning, time may behave more like a dimension of space, so the universe could be finite but without a starting edge, rather like the surface of Earth is finite but has no edge where the surface suddenly begins. This is an analogy, not a direct picture, but it captures the aim, to remove the need for a singular first moment. The no-boundary proposal is not settled fact. It is a serious theoretical attempt to understand the origin of the universe using quantum ideas, but it remains part of an open research landscape. Its value here is that it shows how strange time becomes near the beginning. The question may not be simply what happened at the first second, because the ordinary meaning of seconds may break down. The phrase "before the Big Bang" is therefore delicate. In some cosmological models, it may be meaningful. If time extends through a bounce, or if our hot dense phase emerged from an earlier state, then "before" can refer to a real earlier phase. In other models, time itself begins with the universe, so there is no earlier time to ask about. The word "before" would be trying to reach outside the very thing that gives before and after their meaning. This is where the reality of time becomes especially uncertain. Time is what lets us tell the story of the universe. It orders cosmic history from hot plasma to atoms, stars, galaxies, planets, and life. Yet when physics tries to describe the beginning of that whole story, time becomes part of the mystery being explained. If time began with the universe, then it is not an eternal background. If time existed before the Big Bang, then our visible universe is not the whole temporal story. If time changes character near the beginning, then our ordinary understanding of past, present, and future may be only a late chapter in a much deeper structure. The universe gives us clocks, stars, fossils, radiation, and memories. But when we follow them backward far enough, we reach a horizon where the clock itself becomes uncertain. The deepest problem with time appears when physics tries to put its two greatest theories into the same room. One of them is general relativity. In general relativity, spacetime is not a fixed background. It is dynamic. It bends, stretches, and curves in response to mass and energy. Gravity is not treated as an ordinary force moving through space, but as the shape of space-time itself. Time, in this theory, is woven into geometry. It can run more slowly near massive objects, change with motion, and behave differently depending on the path taken through the universe. The other theory is quantum mechanics. In ordinary quantum mechanics, time usually plays a different role. It is often treated as an external parameter, a background clock against which quantum states evolve. The wave function changes with time. Measurements happen at times. Probabilities are calculated for future observations. But time itself is not normally treated as a quantum object in the same way that position, momentum, energy, or spin can be. Each theory works brilliantly in its own domain. General relativity describes planets, stars, black holes, gravitational waves, and the large-scale structure of the cosmos. Quantum mechanics describes atoms, particles, fields, chemistry, lasers, semiconductors, and the microscopic machinery of matter. Together, they're almost embarrassingly successful, in the way two guests at a dinner party can both be fascinating separately, but become deeply awkward when asked to share one chair. The problem is quantum gravity. Quantum gravity is the still unresolved effort to combine general relativity and quantum mechanics into one deeper framework. It is needed in places where gravity is extremely strong, and quantum effects cannot be ignored, such as the earliest moments of the universe and the deepest description of black holes. In those regions, treating spacetime as smooth and classical may not be enough. Spacetime itself may need to become quantum, and if spacetime becomes quantum, time becomes uncertain in a much deeper way. This matters directly for the question of whether time is real. In everyday life, time seems like a basic ingredient. It is the thing in which events happen. In Newton's physics, it was an absolute background. In relativity, it became part of space-time geometry. But if the geometry of space-time itself is not fundamental, then time may not be fundamental either. It may be something that appears only when the quantum structure of reality is viewed at larger, smoother scales. One famous example of this problem comes from the Wheeler-DeWitt equation, associated with John Archibald Wheeler and Bryce DeWitt. It belongs to an approach called canonical quantum gravity, which tries to apply quantum principles to the geometry of space itself. Very roughly, it asks what the quantum state of the universe would be if the universe as a whole were treated as a quantum system. The strange thing is that, In its most famous form, the Wheeler-DeWitt equation does not contain ordinary external time. It appears to describe a wave function of the universe without the usual ticking background against which that wave function evolves. This is sometimes described as the frozen formalism. The equation seems timeless. Not timeless in the poetic sense of a beautiful song, but timeless in the more unsettling sense that the fundamental description appears not to say. And now the universe changes. The universe's quantum state seems to simply be, rather than evolve according to an outside clock. This leads to what physicists call the problem of time in quantum gravity. The problem is not that clocks stop working in the kitchen. They do not. Toast still burns if left too long, which is perhaps the most reliable domestic proof that some version of time remains operational. The problem is deeper. If the entire universe is the system being described quantum mechanically, then there is no external clock outside the universe. There is no observer standing beyond reality with a stopwatch saying, "Excellent, the universal wave function has now evolved for another second." In ordinary quantum mechanics, time is supplied from outside the system. But for the universe as a whole, outside the system is not available. That makes the usual role of time difficult to justify at the most fundamental level. Some physicists take this as a clue that time is emergent. Carlo Rovelli, known for work on loop quantum gravity and relational quantum mechanics, has argued that time may not exist as an independent background. Instead, what we call time may arise from relations between physical systems. A clock is not measuring time from outside the universe. A clock is one physical system being compared with another physical system. Change is understood relationally. On this view, time may be less like a cosmic river and more like a network of correlations. One thing changes relative to another. A pendulum swings relative to Earth's rotation. An atom oscillates relative to a laboratory process. A heartbeat unfolds relative to the chemistry of the body. Time is not a container holding these changes. It is a way of describing their relationships. Loop quantum gravity, developed by researchers including Rovelli, Lee Smolin, and Abhay Ashtekar, explores the possibility that spacetime geometry itself has a quantum structure. It does not treat smooth spacetime as the deepest level of reality. Instead, smooth geometry may emerge from more fundamental quantum degrees of freedom. If that is right, then ordinary time may also emerge only at larger scales, rather like fluid smoothness emerges from countless molecules, even though an individual molecule is not itself a tiny puddle. But not everyone is comfortable with removing time from the foundations. Lee Smolin, while deeply involved in quantum gravity research, has also argued that time should not be eliminated too quickly. In his view, time may be more fundamental than many timeless approaches suggest. He has criticised the habit of treating reality as if it were best understood from a timeless mathematical perspective outside the universe. Perhaps, Smolin argues, the reality of change and becoming is not something physics should explain away. Perhaps time is not an illusion, but one of the deepest facts we need to preserve. This is why the disagreement remains so sharp. Some approaches suggest time disappears from the most basic equations and reappears only approximately. Others argue that a timeless universe leaves out something essential. The scales involved are unimaginably tiny. The Planck length is roughly the scale at which quantum gravitational effects are expected to become important, though it is not directly observed as a smallest physical pixel of space. The Planck time is the time light would take to cross a Planck length. Again, an extraordinarily tiny natural scale rather than a confirmed tick of the universe's deepest clock. These scales are so far beyond direct experiment that our theories are still guided by mathematics, consistency, and indirect clues more than by simple laboratory access. So the clock begins to vanish exactly where physics most wants certainty. At the edge of black holes, near the beginning of the universe, and in the search for quantum gravity, time stops looking like an obvious background and starts looking like part of the mystery. Some physicists try to make time disappear from the fundamental description. Others think that removing it is a mistake, and between those positions sits the unresolved question at the heart of the title, whether time is truly real or whether it is something that emerges only after reality has become large, smooth, and familiar enough for clocks to tick. Loop quantum gravity begins with a simple refusal. It refuses to treat spacetime as a perfectly smooth stage all the way down. In general relativity, spacetime behaves like a continuous geometry. It can curve gently around Earth, sharply around a black hole, and dynamically across the expanding universe. This smoothness works extraordinarily well at large scales. It guides planets, bends light, predicts gravitational waves, and keeps satellite navigation from becoming a very expensive guessing game. But quantum mechanics suggests that nature may not remain smooth at every possible scale. Energy, matter, and fields show quantum behavior, so perhaps space-time geometry itself must also be quantum. Loop quantum gravity is one attempt to follow that idea seriously. It is associated with researchers including Carlo Rovelli, Lee Smolin, Abhay Ashtekar, and others. Its goal is not to add quantum particles into a fixed background spacetime. Its goal is more radical, to describe spacetime geometry itself as something quantum. This matters because if spacetime is quantum, then time cannot simply be assumed as an ordinary background ticking behind everything. Time is part of spacetime, so if spacetime is not fundamental in the old smooth sense, time may not be fundamental in the old smooth sense either. The basic picture is difficult, but the guiding idea can be stated gently. Loop quantum gravity suggests that the geometry of space may have a discrete quantum structure at extremely tiny scales. Not discrete in the simple sense of little cubes of space stacked like toy bricks, but discrete in a more mathematical sense. Certain geometric quantities, such as areas and volumes, can come in quantum units, rather than varying smoothly without limit. One of the important mathematical structures in this approach is called a spin network. A spin network can be thought of as a graph made of links and nodes, carrying quantum information about geometry. The links and nodes do not sit inside space in the ordinary way, as if someone had drawn a glowing web inside a room. Rather, they are part of what describes the quantum geometry of space itself. Space is not the container holding the network. The network is part of the description of space. A related idea is the spin foam. If spin networks describe possible quantum states of space, spin foams describe how those states can be related through something like a history. Again, the word foam is not meant to suggest ordinary bubbles floating around in a laboratory flask. It is a mathematical image for changing quantum geometry, a way to describe relationships among possible spacetime structures without assuming that smooth spacetime already exists underneath. This is where time becomes subtle. Loop quantum gravity does not simply say time is imaginary, or that clocks are fake, or that your alarm in the morning can be safely ignored for philosophical reasons. Clocks are real physical systems. Alarms, unfortunately, remain operational. The question is not whether time exists in ordinary life. The question is whether time exists as an independent background stage at the deepest level. In many relational approaches, time is not something outside the universe. It is something that emerges from relations among physical systems. A clock is not a magical external ruler measuring time from beyond reality. A clock is itself part of reality. It is a physical system changing in a regular way. When we use a clock, we compare one change with another change. We compare the motion of hands on a dial with the motion of a train. We compare the oscillation of an atom with the duration of an experiment. We compare Earth's rotation with the cycle of waking and sleeping. On this view, time is not a container in which change happens. Time is a way of describing how changes are correlated. Carlo Rovelli has strongly emphasized this relational way of thinking. In relational quantum mechanics, the properties of a system are understood through interactions with other systems, rather than as absolute features existing from nowhere in particular. In his work on quantum gravity, Ravelli has also argued that time may emerge from physical relations rather than exist as an independent background. One especially interesting idea is called thermal time. The thermal time hypothesis connects the flow of time to the statistical state of a system. In ordinary physics, we often assume time first, then describe how a system changes with respect to it. Thermal time tries to reverse the perspective. Given the statistical state of a physical system, a kind of time flow may be identified from the structure of that state itself. This is not an everyday idea, and it should not be oversold. It does not mean a warm cup of tea personally manufactures the universe's time because it feels cozy. It means that, in certain theoretical frameworks, the direction and flow we associate with time may arise from thermodynamic and statistical relationships rather than being imposed from outside. That connects back to entropy. The fact that physical systems have statistical states, that records form in one direction, and that heat and information behave asymmetrically, may help explain why time appears to flow for observers inside the universe. Time, in this picture, is not a universal river beneath everything. It is more like an emergent order found among physical correlations. This is one major camp in the disagreement over whether time is real. It says time may be real, but not fundamental. Real like temperature is real. Temperature matters. It can burn skin, freeze water, shape weather, and decide whether a cup of tea is comforting or mildly disappointing. But temperature is not usually considered fundamental in the same way as microscopic motion and energy. It emerges from the behavior of many particles. In a similar way, time may emerge from deeper quantum gravitational relations, while still being real at the level where clocks, memories, planets, and people exist. But loop quantum gravity remains an active research program, not a completed and experimentally confirmed replacement for general relativity and quantum mechanics. It has produced important mathematical ideas and possible approaches to black holes, cosmology, and quantum geometry, but it has not yet delivered a final theory verified by decisive experiments. That caution matters. The mystery of time is not solved simply by choosing the most elegant-sounding answer. Still, loop quantum gravity shows why the old picture of time as a background stage may be too simple. If the stage itself is quantum, then the clock nailed to the wall of that stage cannot remain untouched. Perhaps time is woven from relations. Perhaps it appears when quantum geometry becomes large and smooth enough. Perhaps it is real in the way patterns are real, not as something separate from the things that happen. Other approaches attack the same problem differently. String theory and holography do not begin with spin networks or spin foams. They bring in vibrating strings, quantum fields, black hole information, and the strange possibility that space-time may emerge from deeper structures of quantum information. Another path into the mystery begins with a very different idea. Instead of starting with quantum geometry made from networks and relations, string theory begins by asking whether the particles of nature might not be point-like objects at the deepest level. Perhaps, at unimaginably tiny scales, what we call particles are better described as tiny vibrating strings. In ordinary particle physics, an electron is treated as a point-like particle, with no known internal size. A quark is treated in a similar way, but in string theory, the basic objects are one-dimensional strings. Different patterns of vibration appear to us as different particles, rather like different notes played on the same instrument. One vibration might correspond to an electron, another might correspond to a quark, another might correspond to some other particle entirely. This is only a broad image, of course. A string in string theory is not a little violin string floating in ordinary space, waiting for a tiny musician with very steady hands. It is a mathematical object existing at scales far beyond direct observation. But the image captures the central idea. Particles may be different expressions of a deeper vibrating structure. One reason string theory became so important is that it naturally includes gravity. When physicists studied the possible vibrations of strings, they found a vibration behaving like the graviton, the hypothetical quantum particle associated with gravitational interactions. This was striking because quantum gravity is extremely difficult to build. In string theory, gravity was not awkwardly added later. It seemed to appear from the framework itself. Important contributors to the development of string theory and related ideas include Michael Green and John Schwartz, whose work in the 1980s helped revive interest in the theory by showing how certain mathematical inconsistencies could be avoided. Edward Witten played a major role in connecting different versions of string theory and shaping the broader framework known as M-theory. Joseph Polkinski made crucial contributions involving objects called D-branes, which became central to later developments. Leonard Susskind also contributed deeply to string theory, black hole physics, and the ideas that led toward holography. And it is holography that brings the question of time into an even stranger light. The holographic principle is associated especially with Gerard 't Hooft and Leonard Susskind. It grew partly from the study of black holes. Black holes have entropy, and that entropy appears to be proportional not to their volume, but to the area of their event horizon. This was a shocking clue. In ordinary life, we expect the information inside a region to scale with volume. A larger box can hold more things because it has more interior space. But black holes suggested that the maximum information in a region might be described by the surface surrounding it. The holographic principle proposes, in broad terms, that the information contained in a volume of space may be describable on a lower dimensional boundary. The name comes from holograms, where a lower dimensional surface can encode the appearance of a higher dimensional image. The analogy is helpful, as long as we do not push it too far. The universe is not simply a shiny sticker on a cosmic lunchbox. The principle is mathematical and physical, not decorative. In 1997, Juan Maldacena discovered one of the most important examples of holography, the anti-de Sitter conformal field theory correspondence. This is often called the Maldacena correspondence. It describes a deep equivalence between a theory of gravity in a higher dimensional anti-de Sitter spacetime and a quantum field theory without gravity on its lower dimensional boundary. The exact setting is not our observed universe. Our universe does not appear to be anti-de Sitter space in the simple way used in the correspondence, so this is not a direct model of the cosmos around us. But it is still enormously important, because it gives physicists a precise example where a gravitational spacetime can be described using a non-gravitational quantum theory on a boundary. That suggests something remarkable. Spacetime itself may not be fundamental. It may emerge from deeper quantum information structures. If space can emerge, then time may also be part of an emergent pattern, depending on the formulation. In some holographic settings, time is still present in the boundary theory. In others, the way space-time geometry arises from quantum relationships raises deeper questions about which parts of space-time are fundamental and which are reconstructed. The point is not that string theory has proved time is unreal. The point is that modern theoretical physics increasingly gives serious mathematical reasons to ask whether space-time, including time, may arise from something deeper. Quantum entanglement is one of the strongest clues. Entanglement links quantum systems in ways that cannot be understood as ordinary local hidden properties. Mark van Ramsdonk and others have explored how patterns of entanglement may be connected to the emergence of space-time geometry. In some theoretical models, changing the amount of entanglement changes the connectedness of space. This suggests that geometry might be built from quantum relationships rather than existing as a simple background from the start. This is exciting, but it must be kept honest. String theory and holography have produced extraordinary mathematical insights. They have deepened the study of black holes, quantum field theory, gravity, and information. But they have not yet been confirmed as the final description of nature. There is no laboratory experiment that has shown vibrating strings directly. There is no decisive observation proving that our universe is holographic in the strongest possible sense. The evidence is theoretical, powerful, and suggestive, but not experimentally final. That distinction matters especially when the question is as large as whether time is real. It is tempting to leap from space-time may emerge in some theories to time is definitely an illusion. But physics does not move responsibly by leaping over the difficult parts, even when the difficult parts look mathematically elegant and have excellent lighting. The more careful statement is this. Some modern approaches to quantum gravity suggest that space-time may not be fundamental. Holography gives concrete examples where a gravitational space-time can be equivalent to a different kind of quantum theory. Entanglement may help explain how geometry arises, and if time is part of space-time, then time may also be emergent in some deep sense. So the disagreement over time becomes wider. One side sees time as a basic ingredient of reality. Another sees time as part of an emergent space-time pattern, perhaps arising from quantum information, entanglement, and deeper mathematical structures. Time still appears in our clocks, memories, bodies, planets, and stars. But in string theory and holography, it begins to look less like the foundation of the universe, and more like something that may be built by the universe from deeper ingredients. Causality is the quiet rule that keeps the universe from becoming nonsense. A cause happens, and then effect follows. A match is struck, and then the flame appears. A star explodes, and then light from the explosion travels outward. A hand pushes a cup, and then the cup moves. This ordering is so ordinary that we rarely notice it, but beneath it lies one of the deepest links between time and physical reality. Time is not only about clocks ticking or moments passing. It is also about what can influence what. If one event can affect another, there must be some kind of ordering between them. The cause must be able to reach the effect. A signal, force, particle, wave, or physical interaction must have a possible path from one event to the other. Without this structure, explanation itself begins to wobble. Physics depends on being able to say, not merely that things happen, but that some things happen because of other things. Special relativity made this more precise through the idea of light cones. A light cone is a way of describing the causal structure around an event in space-time. Imagine a flash of light emitted from one point. As time passes, the light spreads outward in all directions at the speed of light. If this expansion is drawn in a space-time diagram, it forms a cone shape. The future light cone contains all events that the original event could possibly influence, because light or any slower signal could reach them. The past light cone contains all events that could possibly have influenced the original event. Outside the light cone are events that cannot be causally connected to the original event, at least not by any ordinary signal, because reaching them would require something to travel faster than light. These regions are called space-like separated. Two space-like separated events may be ordered differently by different observers. One observer may say event 1 happened first. Another observer, moving differently, may say event 2 happened first. But because neither event can influence the other without faster-than-light communication, this disagreement does not create a contradiction. This is one of relativity's most important subtleties. Relativity removes universal simultaneity, but it does not remove causal order entirely. It says that distant events may not have one agreed upon now, but events that can influence each other still have a stable causal structure. If a signal travels from one event to another at or below the speed of light, all observers agree that the cause comes before the effect. So relativity makes time less universal, but not completely chaotic. It gives up the old cosmic clock, but it replaces it with light cones, space-time intervals, and causal structure. The universe may not have one shared present moment, but it still has rules about what can affect what. This is why causality is so important in debates about whether time is real. Even if the flow of time is hard to define, and even if the present moment is not universal, physical explanations still rely on reliable relationships between earlier and later events. A supernova cannot be caused by the light we observe from it millions of years later. A radio signal cannot arrive before it is sent, A cup cannot break because of a sound it makes afterward. Some order has to be preserved, or physics becomes less like science and more like a very confusing dream with equations. Quantum mechanics complicates the story, but carefully. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published an argument now known as the Einstein-Podolsky-Rosen argument. They were concerned that quantum mechanics seemed incomplete, especially because entangled particles could display correlations even when separated by large distances. Einstein worried about what he called spooky action at a distance. He did not like the idea that measuring one particle could appear to have an immediate connection with the state of another distant particle. This concern touched causality directly. If quantum mechanics allowed instant influence across space, would that undermine relativity? Would it allow messages faster than light? Would cause and effect become unstable? Later, John Bell transformed this philosophical worry into something experimentally testable. Bell's theorem showed that no theory based on local hidden variables could reproduce all the predictions of quantum mechanics. In simpler terms, if particles carry pre-existing local instructions that fully determine measurement outcomes, then their correlations must obey certain limits. Quantum mechanics predicts violations of those limits. Experiments beginning with work by John Clauser and Stuart Friedman, and later especially by Alain Aspect and his collaborators, tested these ideas. More recent experiments have closed important loopholes with increasing precision. The results support quantum mechanics. Entangled particles really do show correlations stronger than any local hidden variable theory can explain. But this does not mean quantum entanglement allows faster-than-light communication. That point is crucial. Entanglement creates correlations between measurement outcomes, but it does not allow one observer to choose a message and send it instantly to another observer by measuring their particle. The individual result of a quantum measurement remains unpredictable. Only when observers later compare their results through ordinary, slower-than-light communication do the correlations become clear. Quantum mechanics is strange, but it does not let anyone use entanglement as a cosmic texting service, which is probably for the best. The universe has enough unread messages already, so causality survives, but in a more subtle form. Relativity protects causal order through light cones. Quantum mechanics challenges our classical intuition about separability and local realism, but it still prevents usable, faster-than-light signaling. The result is a universe where influence, information, measurement, and correlation must be discussed with great care. Some newer areas of research push the question even further. In certain approaches to quantum information and quantum gravity, physicists explore the possibility of indefinite causal order. This is the idea that, in very special quantum contexts, the order of events may not be fixed in the ordinary classical way. One operation may not simply happen before or after another. Instead, the causal order itself may become part of a quantum structure. This does not mean everyday cause and effect has collapsed. It does not mean breakfast can be caused by lunch, or that a forgotten appointment can be repaired by arriving yesterday. Indefinite causal order appears in carefully defined quantum scenarios, not ordinary experience. But it is important because it suggests that causal order, like spacetime geometry and perhaps time itself, may not always be fundamental in the familiar classical sense. That is a profound thought. If the order of events can become quantum in certain contexts, then time may be even less like a fixed background than it first appeared. Yet some form of ordering still seems necessary. Even theories where time is emergent must explain why the world contains stable patterns of influence, why records form, why memories point backward, why signals obey limits, and why causes do not simply dissolve into confusion. This is one reason physicists hesitate to say that time is unreal in any simple way. Time may not be fundamental. It may not flow like a river. It may not provide one universal present. But causal structure is deeply woven into physics. Events are not just scattered randomly through existence. They are connected by possibilities of influence. So even if time eventually emerges from something deeper, that deeper theory must still explain why there is an order to the world. It must explain why light cones work so well, why faster than light signaling is forbidden, why entropy grows in one direction, and why causes leave effects rather than the other way around. The clock may not be fundamental, the present may not be universal, the flow may not be a physical substance, but something must still decide what can happen first, what can happen after, and what can never influence what at all. A strange possibility sits near the edge of modern physics. Perhaps time is not part of the deeper structure of reality at all. This does not mean time is useless. It does not mean clocks are pretending, or that history did not happen, or that you can ignore a deadline by calmly explaining that fundamental physics is still undecided. Daily life remains stubbornly chronological. But at the most basic level, some physicists have wondered whether time might be something that appears only after reality is described in a certain way. The reason is that many deep laws of physics do not obviously need a flowing time. They describe relationships between states, events, or configurations. They tell us how one physical situation is connected to another. They may allow us to calculate change, but they do not necessarily include an independent current of time carrying everything forward. The flow we feel may not be written directly into the deepest equations. This idea becomes especially tempting in quantum gravity. When physicists try to describe the whole universe as a quantum system, there is no outside clock. There is no external observer standing beyond the cosmos with a stopwatch, patiently timing reality from the outside. The universe includes every clock we could ever use. So if the whole universe is the thing being described, time cannot simply be borrowed from somewhere else. This is where the timeless view becomes serious. Julian Barber is one of the best-known defenders of a radical version of this idea. Barber has argued that time may be an illusion, not in the sense that experience is fake, but in the sense that the flow of time may not be fundamental. Instead, what exists most deeply may be a collection of possible configurations of the universe. Each configuration is like a complete arrangement of everything: matter, fields, geometry, and all the relations among them. A gentle analogy is a set of snapshots. Imagine a box filled with photographs. Each photograph shows a different arrangement of a scene. In one photograph, a ball is on the left side of a table. In another, it is in the middle. In another, it is on the right. If the photographs are arranged in the right order, they seem to show motion. But the motion is not inside any single photograph. Each photograph is still. The sense of movement comes from the relationship between the photographs and the pattern they form. Barber's idea is far deeper and more mathematical than a box of photographs, but the analogy gives the flavour. The universe may be made of timeless configurations. Some configurations contain records that appear to point toward other configurations. A brain in one configuration may contain memories of what it calls the past. Fossils, photographs, scars, documents, and starlight may all be records inside a particular arrangement of reality. These records create the impression of a history, even if the deeper structure is not flowing from one moment to the next. This does not mean that nothing changes in the world we experience. It means change may be something reconstructed from relations among configurations. Apparent motion may arise because some arrangements are connected in a way that resembles a sequence. The feeling of passage may emerge because certain configurations contain observers with memories, expectations, and records. The snapshot analogy helps, but it can also mislead. A real set of photographs sits inside ordinary time. Someone takes them, stores them, looks at them, and arranges them. Barber's timeless view is not saying the universe is literally a pile of pictures waiting on a cosmic desk. The point is more subtle. The fundamental description may not contain a flowing time, even though patterns inside it give rise to the appearance of temporal order. This kind of thinking appeals to some physicists because it matches a problem that appears in quantum gravity. In certain approaches, especially those related to the Wheeler-DeWitt equation, the fundamental equation seems not to include ordinary external time. The universe's wave function appears timeless. It does not evolve against a background clock because there is no background clock outside the universe. For a timeless approach, this is not necessarily a disaster. It may be a clue. Perhaps the most basic level of reality is not a story unfolding in time, but a structure from which time emerges. The ordinary world of clocks, causes, memories, aging and motion would then be a higher level pattern, not a falsehood, but not the foundation either. A useful comparison is temperature. Temperature is real. A hot stove can burn you, and a cold night can make you deeply interested in blankets. But temperature is not usually considered fundamental in the same way as the motion and energy of particles. It emerges from the behavior of many microscopic components. In a similar way, time might be real at the level of experience and ordinary physics, while still emerging from something deeper and timeless. Critics, however, argue that this view has serious difficulties. The first difficulty is change. If reality is fundamentally timeless, why does change feel so central and undeniable? Why do we experience the world as becoming rather than simply being? A timeless theory must explain why some configurations contain records of others, why those records are ordered, and why observers experience a direction. The second difficulty is causation. Physics is built around explanations in which earlier conditions lead to later outcomes. If time is not fundamental, the theory must still explain why causes and effect appear in stable patterns. It must explain why a match strike comes before the flame, why a signal is sent before it is received, and why entropy rises in the direction we call the future. The third difficulty is practical success. Time-based physics works extraordinarily well. Newtonian mechanics, thermodynamics, relativity, quantum mechanics, and cosmology all use time in powerful ways. Even if time is not fundamental, any deeper theory must recover the ordinary time we use in experiments. It must explain why clocks work, why equations involving time make accurate predictions, and why the world behaves as if time is real. This is the careful balance. The timeless view does not say daily life is nonsense. Clocks still tick, bodies still age, stars still burn. The kettle still boils before the tea is made, unless the kitchen has become conceptually ambitious. The point is not that time disappears from ordinary reality. The point is that time may not be a basic ingredient at the deepest level. So this is one side of the disagreement. Time may be real as an emergent pattern, but not fundamental as a background stage. The flow of time may come from records, relations, entropy, and the way certain configurations of the universe contain the appearance of history. But not all physicists accept that conclusion. Some argue that removing time is not a breakthrough, but a mistake. On that view, time is not an illusion to be explained away. It is one of the deepest facts physics must preserve. There is another way to answer the mystery of time. Instead of saying that time disappears at the deepest level, some physicists argue that time should be taken more seriously than ever. Perhaps the problem is not that we have trusted time too much. Perhaps the problem is that physics has sometimes tried too hard to remove it. This is the realist view of time. It says that time is not merely a useful illusion, not merely a pattern inside a timeless structure, and not merely a convenient label for change. Time, on this view, belongs in the foundations of reality. The world is not just a complete mathematical object waiting to be viewed from outside. It is a process. It changes. It becomes. New events really happen. Lee Smolin is one of the most prominent physicists associated with this position. Smolin has worked seriously on quantum gravity, including loop quantum gravity, but he has also argued that time should not be eliminated from fundamental physics. In his view, many approaches to physics have been too influenced by timeless mathematics. Equations are often written as though the whole history of a system can be seen at once, from a perspective outside time. But perhaps there is no outside perspective. Perhaps the universe can only be understood from within, as something genuinely unfolding. This is a very different instinct from the timeless view. A timeless approach may say that change emerges from relations between static configurations. The realist view says that change is not something to be explained away. Change is one of the most basic facts we know. After all, the world does not merely contain different states. It moves from one state to another. Seeds grow into trees. Stars form from clouds of gas. Black holes merge and send gravitational waves across space. Life evolves. Memories are made. Choices are faced before they are resolved. Something genuinely seems to happen. The openness of the future is especially important for defenders of real time. From our perspective, the future does not feel fixed in the same way as the past. The past has left records. The future has possibilities. In many timeless or block universe pictures, this openness is not fundamental. It is a feature of limited knowledge, local perspective, or conscious experience. But realists about time argue that this may miss something essential. Perhaps the future is not simply hidden from us. Perhaps it is genuinely not yet settled. Causation is another reason time is hard to dismiss. Physical explanation depends on the idea that earlier conditions help produce later outcomes. A cause is not just placed before an effect in a diagram. It brings the effect about. If time is removed from the foundation, then causation must be rebuilt from something deeper. That may be possible, but it is not trivial. The realist asks whether it might be more honest to keep time and becoming at the centre. Smolin has also explored the possibility that the laws of nature themselves may have a history. This is speculative, and it is important not to confuse it with established physics. The standard view usually treats the laws of nature as timeless. The laws do not evolve. They govern evolution. They are written as mathematical relationships that hold everywhere and every when. But Smolin has questioned whether this picture is complete. If the universe has a history, perhaps the regularities we call laws may also be connected to that history in some deeper way. With the philosopher Roberto Mangabeira Unga, Smolin has argued for a picture in which time is real, and the laws of nature are not simply timeless truths existing outside the universe. Their view challenges the idea that mathematics should describe reality from a God's eye perspective, as if the universe were a finished object laid out all at once. They suggest instead that reality is fundamentally temporal, creative, and historical. This is not mainstream settled physics in the way general relativity or quantum mechanics are. It is a philosophical and theoretical argument about how physics should be understood and where future theories might go. But it matters because it shows that the debate over time is not just about one equation. It is about what kind of thing the universe is. Is the universe more like a timeless structure, where every event is part of a completed pattern? Or is it more like an ongoing process, where the present is real, the future is not yet fixed, and novelty genuinely enters the world? The case for real time has emotional force, but it also faces serious scientific challenges. The first challenge is relativity. Special relativity strongly resists the idea of a universal present. Different observers moving relative to one another can disagree about simultaneity. There does not seem to be one cosmic now shared across the universe. Any theory that makes time fundamental must explain how this can be true, while preserving the tested predictions of relativity. The second challenge is general relativity. Time is not separate from spacetime, and spacetime can curve. Different paths through the universe contain different amounts of elapsed time. A clock near a massive object ticks differently from a clock far away. This makes it difficult to return to a simple picture of one universal time flowing evenly everywhere. The third challenge is quantum gravity. We do not yet have a final, experimentally confirmed theory that combines quantum mechanics and gravity. Some candidate frameworks suggest that time may be emergent or absent from the deepest equations. If real time is fundamental, a future theory must show clearly how it fits with quantum spacetime, black holes, and the early universe. So the realist view is not a simple return to common sense. It cannot merely say, time feels real, so it must be fundamental. Physics has already shown that time is stranger than ordinary experience suggests. A serious realist view must account for relativity, entropy, quantum mechanics, and cosmology. Still, the argument remains powerful. Eliminating time may make equations elegant, but perhaps elegance is not enough. Perhaps a theory that removes becoming, novelty, causation, and the openness of the future has removed something the universe is trying very hard to show us. This is the heart of the disagreement. Some researchers think time is emergent, approximate, or even illusory at the deepest level. Others think that eliminating time cuts away the very core of physical reality. The debate is not between science and fantasy. It is between different ways of taking our best science seriously. Time may be the stage, the process, the relation, the pattern, or the thing that makes patterns become real. And until physics finds a deeper theory that everyone can agree on, the question remains open. After all the strangeness, it is worth returning to something wonderfully solid. Clocks work. They work so well, in fact, that time is one of the most precisely measured quantities in all of science. This is part of what makes the debate so interesting. Physicists can disagree about whether time is fundamental, emergent, relational, geometric, psychological, or somehow incomplete, while still measuring time with a precision so extreme that ordinary language starts to look a little underdressed. Modern timekeeping is not based on the swing of a pendulum or the rotation of Earth. Those were important for centuries, but Earth is not a perfect clock. Its rotation changes slightly because of tides, internal motion, earthquakes, atmospheric effects, and long-term gravitational interactions. The planet is magnificent, but as a timekeeping device, it does occasionally wobble through the assignment. The best modern clocks use atoms. Atomic clocks work because atoms have stable energy levels. An atom can exist in different quantum states, and transitions between those states correspond to very precise frequencies of electromagnetic radiation. If a particular atom reliably changes between two energy levels when exposed to radiation of a specific frequency, that frequency can be used as a clock. Instead of counting the swing of a pendulum, we count the oscillations associated with an atomic transition. The most famous example is the cesium atomic clock. The second is defined using cesium-133 atoms. More specifically, it is based on the microwave frequency associated with a transition between two hyperfine energy levels in the ground state of the cesium-133 atom. In spoken terms, 1 second is defined by counting 9,192,631,770 periods of that radiation. That number sounds magnificently unfriendly, but it gives timekeeping its modern stability. The point is not that cesium atoms know what a second is in some philosophical sense. The point is that the transition is reproducible with extraordinary precision. If laboratories around the world prepare the same kind of cesium atom under carefully controlled conditions, they can use the same physical process to define the same unit of time. Organizations such as the National Institute of Standards and Technology in the United States, the Bureau International des Poids et Mesures in France, the National Physical Laboratory in the United Kingdom, and other national metrology institutes help maintain and compare these standards. Time is not just something on a phone screen. It is an international scientific achievement, continuously measured, compared, corrected, and refined. This is already remarkable. But modern optical atomic clocks are even more astonishing. Optical clocks use transitions at optical frequencies, which are much higher than the microwave frequencies used in cesium clocks. Because the oscillations are faster, These clocks can divide time into even finer intervals. Atoms such as strontium and ytterbium are used in some of the most advanced optical clocks. These systems can reach such extraordinary precision that they become sensitive to tiny differences in gravitational time dilation. That means a clock placed slightly higher in Earth's gravitational field can tick measurably faster than a clock placed slightly lower. In advanced experiments, height differences on the scale of centimeters can matter. This is general relativity brought into the laboratory with almost absurd delicacy. Time does not merely slow near black holes or change for satellites. It changes between different heights in a room, if your clock is good enough to notice. There is something deeply grounding about that. The nature of time may be philosophically and physically mysterious, but the measurement of time is not vague. It is tested constantly. Atomic clocks confirm quantum mechanics because their operation depends on atomic energy levels. They confirm relativity because their ticking changes with motion and gravity. They support satellite navigation, telecommunications, financial systems, radio astronomy, electrical grids, and experiments that probe the foundations of physics. So when physicists disagree about whether time is real, they are not saying that timekeeping is unreliable. They are not saying that clocks are decorative opinions. They are not saying that tomorrow might arrive before breakfast because someone in a philosophy department got ambitious. The disagreement is subtler. It concerns what clocks are actually measuring. Are clocks measuring a fundamental dimension of reality? Are they measuring change relative to other change? Are they tracking motion through space-time? Are they recording correlations between physical systems? Are they revealing an emergent pattern that appears only when the universe is large, smooth, thermodynamic, and filled with records? A clock does not answer these questions by itself. A clock gives intervals. It says that one process is repeated a certain number of times while another process unfolded. It can tell us that a satellite signal took a certain duration to arrive. It can tell us that a moving particle decayed after a certain measured lifetime. It can tell us that a clock on a mountain ticks at a slightly different rate from a clock near sea level. But whether time itself is a thing, a dimension, a relation, or an emergent feature requires interpretation. That is the odd reality of measurement. The more precisely we measure time, the more clearly we see how strange it is. A poor clock can hide the mystery. A superb clock reveals it. It shows that time is affected by speed. It is affected by gravity. It is tied to quantum transitions. It is not the simple background flow imagined in everyday common sense. And yet, because these measurements are so precise, they also steady the whole discussion. Physics is not lost. The mystery of time is not a sign that science has failed. It is almost the opposite. Science has become accurate enough to reveal that the thing we thought was obvious was never obvious at all. Time can be measured to breathtaking precision. Clocks can be compared across continents. Satellites can account for relativity. Atoms can define seconds. Optical clocks can feel the difference between slightly different heights in Earth's gravity. The question is no longer whether clocks work. The question is what kind of reality allows them to work so well. By this point, the disagreement over time can seem almost unreasonable. Time has been an absolute background, a relation between events, an arrow of entropy, a dimension of space-time, a problem in quantum mechanics, a possible emergent feature of quantum gravity, and a deeply felt part of conscious experience. It is no wonder physicists have not simply gathered in one room, nodded politely, and agreed to be finished by lunch. But the disagreement is not chaos. It is not a sign that physicists have no idea what they're talking about. Very often they agree on the equations, they agree on the experiments, they agree on what clocks measure, what relativity predicts, how entropy behaves, and how quantum systems are calculated. What they disagree about is interpretation, meaning, and ontology. Ontology simply means what a theory says exists. It asks what the mathematics is really describing. Is time a thing in itself? Is it a dimension? Is it only a relationship? Is it a feature of experience? Is it a higher level pattern emerging from deeper physics? These are not always questions that experiments answer directly, at least not yet. They sit at the boundary where successful equations meet our attempt to understand what kind of universe those equations are showing us. The old view begins with absolute time. Isaac Newton treated time as a universal background flowing evenly everywhere, independently of objects, events, and observers. This made classical mechanics extraordinarily powerful. Motion, acceleration, gravity, and planetary orbits could all be described against one shared cosmic clock. In this picture, time is fundamental and external. It is the stage on which the universe changes. Gottfried Wilhelm Leibniz challenged that picture with relational time. For Leibniz, time was not an independent container. It was the order of events and changes. One thing happens before another. One process unfolds alongside another. If nothing existed and nothing changed, there would be no meaningful time. This view still echoes in modern physics, especially in approaches where clocks are understood as physical systems compared with other physical systems, not as windows onto an invisible universal flow. Albert Einstein and Hermann Minkowski transformed the debate again. In special relativity, Einstein showed that time depends on motion, and that there is no single universal present shared by all observers. Minkowski then joined space and time into four-dimensional spacetime. This encouraged spacetime eternalism, or the block universe view, where past, present, and future may all be part of one complete spacetime structure. In this view, time is real, but not as a moving river. It is a dimension woven into geometry. Thermodynamic time adds another layer. Ludwig Boltzmann showed that the second law of thermodynamics can be understood statistically. Entropy tends to increase because high entropy states are overwhelmingly more probable than low entropy states. Roger Penrose later emphasized how strange the low entropy early universe appears, especially when gravity is included. This view does not necessarily say time flows as a substance. It says the direction we call the future may be tied to entropy, records, memory, and the special boundary conditions of the universe. Quantum mechanical time creates a different puzzle. In ordinary quantum mechanics, time is usually treated as an external parameter. It is the background against which the wave function changes. But the measurement problem complicates the story, because quantum systems evolve smoothly according to the Schrödinger equation, and yet measurements produce definite outcomes. Time becomes tangled with probability, observation, collapse, decoherence, and what counts as a real physical event. Then quantum gravity deepens the mystery further. John Archibald Wheeler and Bryce DeWitt are associated with the Wheeler-DeWitt equation, where the wave function of the universe appears to lack ordinary external time. This leads to the problem of time. If the entire universe is being described quantum mechanically, there is no outside clock. No cosmic laboratory assistant stands beyond the universe with a stopwatch and a clipboard, which is inconsiderate but understandable. Carlo Rovelli and other researchers in loop quantum gravity explore relational and emergent views, where time may arise from correlations between physical systems rather than exist independently. Julian Barber has argued for a more radical timeless view, where apparent motion and history arise from relationships among configurations of the universe. In these approaches, time may be real at the level of experience and ordinary physics, but not fundamental at the deepest level. On the other side, Lee Smolin argues that time should not be removed too quickly. For Smolin, time may be one of the deepest features of reality, not an illusion created by a timeless structure. He has suggested that change, novelty, causation, and the openness of the future may be too important to explain away. Stephen Hawking's work with James Hartle on the no-boundary proposal gives yet another angle, where time near the beginning of the universe may behave in ways unlike ordinary time. Each view tries to take the physics seriously, but they do not all lead to the same conclusion. This is the central point. The disagreement is not usually between people who understand physics and people who do not. It is between serious attempts to interpret theories that work extremely well. Newtonian mechanics still works beautifully in everyday conditions. Relativity has been confirmed by time dilation, gravitational redshift, satellite navigation, black holes, and gravitational waves. Quantum mechanics is tested constantly in atoms, lasers, semiconductors, and particle experiments. Thermodynamics remains one of the most reliable frameworks in science. The problem is not failure. The problem is that success points in several different directions at once. Time works brilliantly in measurement. Atomic clocks can define the second with extraordinary precision. Time bends in relativity. It slows with speed and gravity. Time points one way in thermodynamics through entropy, memory, and records. Time behaves strangely in quantum theory, where it often appears as an external parameter rather than a normal observable. And time may even disappear, or at least change beyond recognition, in quantum gravity. That is why physicists still cannot agree on whether time is real. If real means useful, measurable, and unavoidable in experience, then time is absolutely real. If real means fundamental, independent, universal, and present in the deepest possible description of nature, then the answer is not yet known. Time may be a basic ingredient. It may be an emergent relation. It may be a dimension of spacetime. It may be a thermodynamic direction. It may be a structure of causality. It may be partly shaped by consciousness. Or it may be something we have not yet learned how to describe. The safest answer is not simple, but it is honest. Time is real enough to organize experience and physics. It is real enough for clocks, stars, aging, memory, gravity, satellites, and the history of the universe. But its deepest nature remains unsettled, and that uncertainty does not weaken physics. It shows exactly where physics is still awake. Physicists still cannot agree on whether time is real because the word real does not mean just one thing. In everyday life, time is real because we feel it. We remember the past, anticipate the future, age through the present, and experience life as a flowing sequence of moments. In measurement, time is real because clocks work. Atomic clocks define the second with astonishing precision. Satellite navigation depends on relativistic corrections. Light, gravity, motion, atoms, and energy all reveal time as something physics can test again and again. But in the deepest theories, the answer becomes less simple. Newton treated time as absolute, a universal background flowing evenly everywhere. Leibniz challenged this with relational time, where time is not a container but the ordering of events and changes. Entropy then gave time an arrow, showing why tea cools, stars burn, bodies age, and records point toward the past. Special relativity broke the universal clock, making time depend on motion. Minkowski joined space and time into spacetime, encouraging the block universe view where past, present, and future may all belong to one four-dimensional structure. General relativity made time even more physical, because mass and energy curve space-time and gravity slows clocks. Quantum mechanics then treated time differently, often as an external parameter, rather than an observable like position or momentum. The present moment became difficult to define, because relativity gives no single universal now. The flow of time became difficult too, because equations often describe relations between events without adding a separate substance called passage. Cosmology pushed the question back toward the beginning of the universe. The Big Bang model describes a hot, dense early state, but whether time itself began, there remains uncertain. Quantum gravity made the puzzle deeper still. In approaches such as the Wheeler-DeWitt equation, ordinary external time seems to vanish. Loop quantum gravity suggests time may emerge from relationships among physical systems and quantum geometry. String theory and holography suggest space-time may arise from deeper quantum information structures. Causality keeps the story grounded, because even if time is not fundamental, physics still needs some ordering of influence, cause and effect. Some thinkers, such as Julian Barber, argue that time may be part of a deeper timeless structure. Others, such as Lee Smolin, argue that time is real and should not be explained away. Atomic clocks then bring the whole mystery back down to earth. Time may be conceptually unsettled, but it is measured with breathtaking precision. So the careful answer is this: time is undeniably real, as something experienced, measured, and used in successful physics. But it may not be fundamental in the deepest theory of nature. A future theory of quantum gravity may reveal time as emergent from relationships, information, entropy, quantum geometry, or something not yet imagined. Or it may restore time as a basic ingredient in a new and more subtle form. No interpretation has won completely. Every clock, heartbeat, sunrise, orbit, and memory may therefore be part of a mystery that physics understands with extraordinary precision, yet is not completely explained. Time is not less wonderful because it is uncertain. It is more interesting because it sits exactly where experience, mathematics, and reality meet. Reality